as we have known the engine bracket in the last session, we have tried for one case. With that, we have done for your modal analysis, right? So, or else I'll take step by step each thing. So first I'll take modal analysis, and then static. For this again I'll click on to second load case, that will be horizontal. Third load case, that will be vertical, sorry, inclined load case. And the fourth load case will be combination of all the three load case. Okay. So first I'll import a geometry, import, browse. I'll go back to your beam folder. You can see original STP. Now right click on that, your geometry has been updated. Now open your model mechanical editor. Okay, now you can see your geometry has been updated, right? Now you go back and check your geometry, which material, it is structure steel. Now you need to change it, but you can't change here. So what we'll do back, what we'll do, we'll just do the other thing and we go back, or you can change at this point. So general material, tungsten alloy, either you can directly change or what the requirement you have in your, you can change the requirement of your titanium alloy, that is titanium, your Young's modulus, Poisson's ratio and density. If you change these three, you'll get all the other things as updated. Only your yield and strength, these will not be taken into account. You are concerned about density, Young's modulus, Poisson's ratio, buckling, shear modulus. Okay, bulk modulus and shear modulus. These will be updated automatically. If not, I'll show you how it will be. So what is your, it is in 1.13 GPa. Okay, so 11. So I'll add to this. So engineering source, either you can take this or you can write it as tungsten 6 aluminum Ti6Al4. Okay, so you can either do this or this way. So I will just add up with the properties, density and your isotropic elastic. Yeah, other things are updated directly. So I'll take this as directly a density value that is same as the tungsten alloy. I'll take this, add up here. Okay, and then your Young's modulus, it is 113.83 GPa. Okay, your Young's modulus and your Poisson ratio is 0.3. So once these are updated, so go back, sorry, so go back to project, refresh project, and then go back to your material applied. Go to material, you go for 10 see that your material is updated. As previously, one of you were getting an error, check to your geometry. That is because your geometry would not have taken any effect of material, or your material has not been assigned properly. That would be one thing. Or that your geometry, whatever, while importing, that is from the CAD, you are importing your STP file to Ansys. That time your CAD might have some defeatured component which are not closed or enlooped correctly. At that time you might get those errors. Okay, so that is might be a one case. So next, the coordinate system, I'll just update the coordinate system as two coordinate system, that is one as CS1 and second would be as inclined coordinate system. I'll be taking as inclined. Okay, and next for mesh, I need to update the mesh. How do I take it? I'll go to sizing, I'll take this adaptive to proximate and curvature. Here all the values are taken into default, or else I'll go for adaptive and I'll go for medium or fine, anyone you can take. Okay, so if you take that and you are keeping your element quality yes, only errors, if warnings you require, you can check what typically minimum element it is there and other things. Okay, so then you just give an update. Now sorry, generate mesh. Your mesh will be updated. You can see your mesh. Okay, typically at the critical areas, you can see at the critical, these are the critical one. At that positions, like your, you can see that your fillets are filled with one or two elements minimum. Okay, so because of, you can also see at this position, because the fillets are more critical in our design and designing. So that's why we require more concentrate on the fillets, whether they fail or what changes we need to do. So minimum of two elements will be selected at that region. So your software will automatically update that fillets as number of elements of 2. Okay, this is what the speciality of Ansys. So it will automatically reads your geometry and give the requirement based mesh. So your mesh is updated. Now I'll update your coordinate systems. One is, I'll select these both the surface, that is of your coordinate system. With respect to that, x-axis or y-axis I'll take as geometry selection. So once it is updated, you can see your coordinate systems. This is one. And the second one, how do we assign that coordinate system? Now go to inclined coordinate system, select same faces, apply. As you can see, now we require this, as mentioned in the presentation, we require the inclined loads. 3 loads were there, sorry, not in this presentation, the other one. Okay, we require the inclined 42° from vertical. So now you need to check which will be your vertical. The first, I'll assign this same as this, selection as surface as the selection. So you can see your vertical becomes Y. Guys, today there are 15 members. Has anyone joined twice or is no, it is 14. Okay, fine, no issue. So you can see your coordinate system as y as vertical. Now from y we require 45 to 45 degree. So how do we select that? So we take ry, sorry, it will not be there. Sorry, rx, consider rx.
You have to rotate with respect to x-axis.
Yes, 45 to 45 degree, negative 45 degree. Please enter as negative because your y is below. So you can see that 42, 48. Hold on a second. So z will be with respect to x. Okay. So this will be a coordinate system. Either you do this way or considering your y geometry, the selection of geometry as.
Sir, can you do that again, sir?
Yeah, sure. I'll just will delete it. You can see I'm inserting one coordinate system, that is I'll rename it as inclined. Okay. Then selecting the inclined coordinate system, how do we select it or generate it? So I want my coordinate system between the lugs. So I'll select the lugs. It will automatically generate the coordinate with respect to your global coordinate system. You can look as same as your global coordinate system they are been representing. Yes. Now I want these to be vertical and from there I require 45 degree. What I'll do, I'll select my x as geometry selection and select the base or okay, now you can see your x axis is below or I'll select this as the vertical line. The edge as the vertical line. Your geometry selection. Okay. So now your x will be the vertical line. So it is showing as downwards. Okay. So change the direction. It will be upward. Your x will be in upward direction. Now I want to rotate this to the x into 45 degree. How do I do it? So I'll take RZ because your RZ, your rotation should be with respect to RZ. So I'll rotate this RZ with 45 degree, 42 degree as mentioned. Oh, sorry, negative 42 degree. So you can see your x axis with 42 degree inclined. Either it may be similar with Z, but your angle is required. You should ensure that your angle is correct. Okay, as that the requirement of the customer. Okay, understood? Any doubt here?
Sir, how do you like? Why did it be 42 degrees? Sir, was it mentioned in the question? Angle.
Sorry.
Sir, the 42-degree angle, sir. How did you got to know? Sir? Was it mentioned in the question?
Yeah, it is mentioned. You can say that the loading condition, third loading condition, that is your inclined load is applied at 45 degree, 42 degree from vertical. From vertical, it has been applied at 42 degree. It has been given from the customer. Okay. For that, we are applying our load at 42 degree from vertical. Okay. Any doubt again?
No, sir. No, sir.
Okay.
Got it.
So then your mesh has been updated. Now for the model, if you run, or I'll make one more duplicate of this. So it will be at the last. If you run it directly, I'll just take a deformation and run directly, or settings, I'll increase by other 2. That will be your free run, your free modal analysis. Okay, and then apply a boundary condition for the same modal analysis. That becomes your fixed modal analysis. As the geometry is 1, so you'll surely get 6 0-degree mode, and the 7th one will be having a positive value. As you can see that the first 6 are values are equal to 0, and the 7th and 8th have a positive value. Even you can select all, you can generate the mode shape, just give evaluate results. So you can check all the 6 modes as in 0 hertz or 0 frequency, and 7th mode will be having a positive value frequency. Okay, so this is your free run. The same thing, everything is same, applied everything. Again, I am taking here only 8 or 9 modes, and then I am applying a boundary condition, that is fixed support. So where the fixed support of this component fixed support is at a your bolt regions. So your bolts are arrested in all the 6 directions. So that becomes your fixed support as a boundary conditions. Okay. Then you require how many frequencies, natural frequencies? You have given as 8. So we will solve this free or fixed modal analysis to calculate the natural frequency of the component. So now you got a natural frequency of your component. What I'll do, I'll just select all, create all the mode shapes, then evaluate your mode shape results. So mode 1, 2, 3, 4, 5, 6, 7, 8, 9. All the 9 mode shapes you are seeing. So first, for the low, your body will be in wireframe. I'll take let's say wireframe. You can see your first mode, and second mode will be in other directions. Okay, third mode. Okay, so similarly, moving further with static analysis, you require to apply a boundary condition and then apply loads. Here load will be considered as bearing loads, because the bearings loads are acted by the other shaft or the other bearing or bracket which is attached to using your shaft. Okay, so that what I'll do, I'll consider the fixed support as
Sir,
the same
excuse me, sir.
bolt holes. Yeah,
So like in the previous case, sir, prior to this where you didn't apply any forces, no, sir. Like you
yes,
just fix the component and then
yes,
these cases, sir.
yeah.
Like why will there be any deformation, sir, if no our load is applied?
See, deformation is for self-excitement. It is like you're doing an experiment of your uh, phoning tube or your pendulum. So you're giving initial excitement. Okay, your body is moving. With per respect to time, how much oscillation it is taking, you are taking into account. Similarly, your software will excite a self excitement and solve for that. You understanding? For that, your displacement values or the magnitude of your pendulum with self excitement. So that is what it is mentioned.
Sir, what do the different modes indicate, sir? Like you have created
Different
10
modes in the sense how your body behaves in particular directions. First, I'll consider your mode shape as 1. You can visualize keeping in a particular directions, or I'll say you can visualize here. I'll increase the scale little bit so that you'll be having more clarity. See, in a first shape, you're having a magnitude of 68. Your frequency is 38156. Okay. In this direction, it has a displacement or the highest magnitude, amplitude, what we call, and the number of oscillations are this much. Okay. In the second one, you can see your entire is in this direction now. Your loads are applied in this direction and the magnitude is 43 with your 42349 as your frequency, natural frequency in this mode. As again for third, it will change again to other direction. Now you can see it is in this direction. Okay, in this direction the frequency is, or the magnitude is 296 with the frequency of 54832 hertz. So each mode shape shows you in different how your component behaves for the self excitement. You understand? So that is what the mode shapes are. That is what your mode shapes are mentioned for, or we can say your mode shapes behavior, the model behavior we are checking here.
Okay.
Yes. Okay, so next, further moving, we are applying a fixed support. Okay, then you are applying a bearing load on each lug. I'll apply a bearing load on each lug with the component with the coordinate system CS1, because I'm consider this okay. This is from the other batch. Okay, you can see this. For one, that is initially I'll consider this load case as vertical. Horizontal, inclined, combined. Okay, so each load case I am saying. So for this vertical, in the sense I'll be applying my load in negative y direction because it is vertical above. So y negative, what is the value of applying that? Will be 8000 lbs. So that 8000 lbs convert to your Newton per Newton. So it will be 355,857. So divide by 2 because your 2 lugs are there. So applying 2, so it will be divided by 2. So your value will be 17792.885 Newton. So for each negative direction, you are applying the value. Yes. Now for the bearing supports load second, I'll select the geometry and again I'll select the vector defined by coordinate system, that will be CS01 and the value would be negative and upward direction. So now you have applied boundary condition, bearing loads 1 and 2, and you are requesting for output as total deformation, stress. If you also want strain value, you can strain value. Even if you want maximum principal stress or shear stress, nominal shear stress, and maximum principal stress would be 1 fine. For that, you need to give as solve. Now your problem has been solved. Okay, so now you can visualize your displacement. So I'll take this to a true scale, how much displacement it has been and how much equivalent stress it is. Where is your maximum stress? Where is your elastic strain value and your shear stress, maximum principal stress, all the things that has been calculated. Similarly, now again, insert fixed support, or what I can do, I will delete this, or you can directly duplicate this. Okay, which will your reduce your, so I'll rename it as horizontal 01, which will reduce your effort, that is applying each time fixed support, bearing loads, other things. So now how do you do it? Now you have taken the horizontal, you need to apply this in horizontal direction, that is your negative z direction. So negative z direction, what is the value we need to add? That is 3708.88. so divide by 2, so 18904.94 will be applied in negative z direction, and your x direction component will be removed or made written as 0. Okay, now your load is applied in opposite direction. What I'll do, similarly I'll apply for your, sorry, this value will be 0 and I'll be applying for z direction. Hold on a second, guys. Sorry for the disturbance, guys. Okay, so I have applied the z direction, that is horizontal load. Now again I'll solve the same thing, everything is same here. Boundary condition, once I keep here your fixed support, bearing load 2, your load has been updated and it has been fixed, and your outputs are called, that is total deformation, equivalent stress, other things. So what I'll do, I'll just give a solve. Again your horizontal problem is being solved easily. Yes, now you can see your deformation, your stress, bonus stress, your equivalent strain values, shear stress, maximum principal stress. Okay, next, same thing I need to do for inclined. What I'll do, I'll click on duplicate. Here again one more duplicate of horizontal has been generated. I will rename it as inclined. Okay, inclined 01. Then your fixed support will be same, your boundary condition will be same, your bearing loads need to be changed. Your bearing loads, how do you convert your, for the previous I have not explained. Okay, 9500 lbs, convert that to lbs to your newton. So 1 newton is equal to how much lbs? That is 1 second, let me check. So 1 lbs is equal to 93.4. 93.41 Newton. Okay.
Excuse me, sir.
Yeah.
Is it LBF or LBS, sir?
LBF and LBS are one and the same.
Sir, actually, one LBF is equals to 4 point something Newton, sir. So only as
LB? Yes, you're talking about. So this is pounds. Newton to pounds, you're talking about LBF, you're saying, right? Let me check once. No, it is pounds per feet. Okay. LBS and LBF doesn't make much. You can see this pound per force. Okay. 4.48. No, as the conversion might change. It is if I consider 9,500, right? The values are 9,500 LBS out. Okay. If I consider this, LBS, that's what I have seen. Like LBF or LBS are one and the same. So this conversion will be the factor 4.45. So what we considered here 93.41. Okay. Let me check that, because LBF, as I have worked on this, LBS and LBF are one and the same. Only per unit square feet something they are considering for LBF and LBS, the difference. Okay, just go back and cross check once you also. Okay.
Sir, LBF is 4, sir. Like, but LB
Yeah,
is
that's
weight.
what pounds per force, and LBS.
Like, how do you you convert kgs to newtons by multiplying this by 9.81?
Okay.
You convert LBS to LBS by multiplying this by 9.81.
Okay, fine. Okay, I understood that. Okay, so our value will be like 4.45. You're taking as multiplying with so 42,000. This divided by 2, because each load. So your lug load force values will be like 21,137.5. Okay. So now you're applying your bearing loads in vertical direction. So the vertical direction will be the component, and your coordinate system will change to inclined. So that will be your positive x direction. Your positive x direction, your z will be becoming 0. Okay. Similarly, for the other load, your z x will be having, you need to change your coordinate system. So now you can see here all the three loads, all the two loads of your inclined. Okay. So now again your fixed support is there, bearing load 1 and 2 are applied. Now you can get your total stress values, or displacement stress, maximum stress and minimum stress values. Now you can see again total deformation, equivalent stress, equivalent strain value, shear stress, maximum principal stress value. Now the combined load cases. The combined load cases in the sense, here I'll insert or I'll take as a duplicate, or you can write it as combined load. So here you need to, your boundary condition will be same. The bearing loads, you need to multiply these bearing loads or insert new bearing loads. Okay, so one, now make it as duplicate, duplicate, duplicate. So totally 6 bearing loads will be there. You can write it as, this will be inclined 1, second will be inclined 2. Now third one, you need to decide vertical, sorry, vertical 1, vertical 2, and third will be horizontal 1 and horizontal 2. Now for inclined 1 and 2, it has already been assigned. So vertical, you need to select the which face you want to, or which lug you want to apply, and then vector, remove that and make it as coordinate component, then global to CS01. Now the value, which value it will be, your first vertical value. So I'll go back, the initial after your, so negative y, okay. Same similarly, now it is applied vertical. Same similarly for vertical 2, select the other lug, apply, change the word vector to component, global coordinate system to CS01, and then enter. Now your both the lugs with vertical, it has been applied. Now next comes your horizontal. So we'll go above and select the horizontal load, what it is. So it will be Z. So horizontal, select the first lug, change to vector to component from global to CS01, and apply the load to Z component, so that your horizontal is applied correctly. Similarly for the other lug, apply, change the coordinate vector to component and global coordinate system to CS01, and then apply the load. Now you have applied all the 6 loads with your fixed boundary conditions. So you can see this clearly, your 3 loads has been applied, vertical, horizontal, and inclined loads has been applied. From this you request for solution, solve F5. Now you got a solution. So this is like deformation of all the combined loads. This will be your stress, that is one versus stress. This will be your strain value, shear stress, maximum principal stress. From this you need to calculate your margin of safety or factor of safety while comparing with your yield strength. So what is your, going back to material property, your yield strength is 903. So which will be your more critical load case? Your more critical load case will be your combined load case, because all the 3 are applied. So check for the one misses, it is 891.5. Now you can take this, your value is, sorry, your what we call yield is 903.21 is your yield point. and your maximum shear will be, your maximum stress will be how much? 891.5. So what will be your factor of safety? So it will be divided by upright. So your factor of safety is 0.0131. Okay. So which will be your critical zone now? How do you identify your critical zone? For a combined load case, your lugs are more critical. Your lugs as well as your bolted region, or you can ignore the bolted region because of they are constrained. So you can consider your lug as a more critical regions because it has a margin of only 1. Your locations are, your values are being passed, or your component is passed for yield, but it is having very less margin. You can see here, you can apply minimum, maximum. So you can see your maximum stress is at your one of the lug, and the minimum is at your base, or somewhere it has more geometry or more thickness. Okay. And if you want somewhere,
can you repeat the factor of safety calculation?
yeah, see, for the factor of safety, your yield, you can see the yield point, yield strength is 903.21 MPa. Okay, so that is what I have taken here. 9, I'll just remove this. So 901 is your yield value. Yes, yield strength. Yes, and your applied stress, that is your von Mises stress, is 891.5, which you got from the solving for the combined load case, which we consider as a more critical load case. Okay, so for this I'm calculating, that is 903.21 divided by 891.5. I'm getting my factor of safety is 1. That means it is passed. But your margin of safety, or what is the margin you are applying, it is just the value minus 1. So you have only, we say this is pass, but it has very less margin.